Hello! In this tutorial, I'll be showing you how to prepare your input files for melt modeling calculations using the PyUserCalc package of melt models in Python. There are two sets of models in the code package that can calculate the outcomes of partial melting. The first and overall focus of the package determines U-series disequilibria in partial melts during progressive melting by porous flow. The second does the same, but for stable element trace element calculations. Both models can determine a range of chemical equilibration during melting using different transport regimes, but these can all be determined during a single run and using the same input files, so the choice of transport regime is actually made later. There is a separate tutorial that explores how to install Python and Jupyter using an Anaconda distribution, and it's also possible to run the code for PyUserCalc using the Enki Jupyter Hub cloud environment. I'm not going to focus on that here. I will instead just show you how to manually or automatically generate input files to do the calculations you want. First, I'm going to show you some input files themselves so you can see how they are formatted. These are comma-delimited text files, or CSV files, like the ones shown in the list here. I usually view and, if I need to, edit them in Excel. For the model to work the way it is written in the Jupyter Notebook code files, all of your input files should be stored in the data folder in your PyUserCalc directory or cloned repository. As you can see, I have many input files that I've set up, both for testing, some of these sample ones I've run many times for model development, and also for some of my own research. So I'm going to show you a couple files. This first file is for U-series calculations using the main PyUserCalc code. These have the same basic format as input files from the old UserCalc of Spiegelman 2000. But now you can include a comment row, which is helpful. The code needs to know to ignore this comment row so that it can find all the columns and headers successfully. So be sure you start this row with the word comment. It will actually look for that so it knows to ignore this row when looking for the headers. The rest of this file has pressure steps in kilobars, here starting at 40 kilobars and going all the way to the surface at 0. You could stop earlier than 0 if you'd prefer, or if that's all you have data for. The rest of the columns are input vectors that vary with depth or pressure. So these should be constant pressure steps. Everything else, they do not need to be constant. They do not even need to be linear. So for example, F is the degree of melting from 0, no melting has occurred, to the maximum degree of melting, which is here 20%. They should be in decimals. Kr is the reference permeability, scaled to a value of 1. It's explained in more detail in the PyUserCalc manuscript, Elkins and Spiegelman. In this example, it isn't changing because I am not studying it in the sample template, but you can put other values in this column. For U-series calculations, you also need values for all 4 of the U-series elements that are considered in the model, uranium, thorium, radium, protactinium, that are bulk partition coefficients, so that the model knows how all of the different nuclides partition from one another as melting proceeds. There's also a stable element concentration tool that is set up similarly, and can use as many elements as you want. Even, actually, you could write in fictional elements if you just want to name them A, B, C, D, or something like that for testing. Here I've put in real elements, but not real numbers, because this was a test template. But any number of elements is fine. This input table is otherwise very similar to the one for U-series, except you don't need the KR column, because it's not important and is not used for stable element concentration calculations. If it is included, it will just be ignored, so it's not harmful to have it in here, but you don't need it. The only thing that really matters for your file formatting is that you have your elements listed in the headers for the partition coefficients. So if you write this file manually, they should all have D at the start, capital D. The reason is the code needs to identify which columns are elements, and it does so by looking for the D value. Otherwise, this is just a simple test template, and obviously these numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, are not logical. They were just there because I was testing the model setup. I actually generated this file input using our template generator, which I will also show you today. Let me get rid of these so I can do that. So the original PyUser Calc package included a 2-layer model notebook, which is called 2-layer model. Right now we have version 2.0 because I've made some updates to it. There are also some functions in the usercalc.py driver code that would produce input files using the template. We've made some updates all around, including generating stable element concentration calculations, and therefore I also wrote an amended version of the functions for generating stable element input files that are in the stablecalc.py driver script. But it's all quite similar to the original version. If you open this notebook, it's quite short. It has some explanation in line though, and basically you just need to give the code a few pieces of information to construct a model and generate an input file for you. So you will give it, for example, a number of rows like these here. So I can actually run this for you and show you what happens. If you want more detailed information, removing the comment here will print a whole bunch of information to the screen for you so you can read about it. That's generated by the driver script. But we'll turn that off. We don't need it right now. There are a couple different tools. One is for U-series, one is for stable element. You can do one or the other or both. Either way, you need to have a certain number of rows, a certain pressure range, and then you need to have a boundary layer where you're going to create a second layer. This is going to generate a 2-layer template with a bit of a transition zone between the two. This smoothing parameter, which I usually do not touch, simply defines how you smooth between the layers to produce a continuous range. And the next cell defines my degrees of melting from the base to the top of the column with, again, an inflection point. What it will do is use this information to create 2 layers of constant melting rate. Now, it is not necessary to give usercalc constant melting rates. You can have them vary nonlinearly, but the template is simpler, so it will generate simple, basically constant slopes. Now we're going to give it a name. I've already named one this, so I'm going to call it Test 2-Layer Model. That's fine. And I'm going to now give it, for the U-series tool, a few additional pieces of information, like the KR values. I'm going to make them all 1 for simplicity, just like in the example I showed you. And then lower and upper layer constant bulk partition coefficients. Again, the template is simpler. The model does not require constant partition coefficients overall or within each layer, but for the template, that's the way this one is set up. So they need to be in the order uranium, thorium, radium, protactinium when you give it these values. Now you can look at what you did, and this just gives you the top 5 rows so that you can see if it looks approximately right, and then you can generate a figure to see, this input file looks like what I pictured it would. And then you can export that by saving it to your data folder. You can also do the same. I will call this test stable model, so I don't overwrite what I've already done. Just like before, I have a list of information to give the tool. Now, this time I can give it the list of any elements I want. They need to be in quotes, and they need to be in the order in which I want them to be listed. Then I will give it the lower and upper bulk partition coefficients. These also need to be in the same order to match the list of elements as above. And then I can observe a list of those to make sure I entered them correctly. I added this because it's enough numbers, it's easy to mix them up, and this way you can double check that you did it right, and if not, go back and fix it. Then we're going to see what that looks like for the top few rows and generate our very artificial test figure. And finally, export these results. And that's it. That generated inputs that actually look exactly the same as some of the templates examples that I showed you in the beginning of this video. What this leaves out is how you might actually decide on reasonable values for inputs for all of these calculations, whether relatively simple ones, like the values to use in your different layers in a very simplistic template, and what slopes you would want for the degree of melting with pressure. Or if you want to do something far more complex, by allowing for nonlinear variations and setting up your own input files manually. That's a much more scientific question that depends on your research goals and what you are trying to solve. We can make some recommendations for that in separate tutorials, and we may, but ultimately that ends up being up to the scientist based on what you want to determine. I think that's it, but good luck and happy calculating.